Hello. Our topic for today is section 1.3, which is valid and invalid arguments. So basically here we have the everyday life side of the story and the formalist side of the story. So what is the argument? So argument is a sequence of statements. Let's call these statements A1, A2, A3, A9. In that sequence of statements, we are assuming that all the statements before the last one are called the premises, and the last one is called conclusion. So generally in the argument we kind of list some statements, and at the end we conclude that what we provided among the premises actually justify why would the conclusion be true. In order to formalize this, we have actually an abstract version of this, and that is called the inference. So what is the inference? Our premises are not statements anymore, they are propositional formulas. So F1, F2, let's say Fn minus 1, and the last one is Fn. We put here, for example, one of the symbols is 3 dots to kind of separate the conclusion from the premises. And the same way as in the first two sections, we are, for practical purposes, we are interested in the arguments, and then that's why we formalize inference. But we want to formalize that process so that it's easier to check if an argument is valid. Or, if the argument is, let's make a distinction, although they are not really that precisely formalized. Let's say, so we are interested in if argument is correct. So in order to check if an argument is correct, what we do, we formalize it as an inference and then ask, is the inference valid? Is the inference valid? This is very conditional. Here saying valid, here saying correct. We obviously use it interchangeably. So, so when do we say now that the inference is valid? Now, since this is a formal definition, then we can also make this more precise. So is the inference valid? So here's the definition. An inference is valid if, whenever all premises are true, the conclusion is also true. Here is an example. I will do it here and I will erase the board. Example. Here is one famous inference. Just P. P implies Q. Then we have Q. So I'm asking you, is this a valid inference? And you can very easily justify the answer is. So is a valid inference, is valid. Why? Because we will very easily make a table then what happens in that table? We have to use the table very carefully. P implies Q. So then, here is T, F, F. And then we know the table from last time. This is true, this is false, this is true, this is true. So question is this a valid inference? So definition says, in order to say that this inference is valid, we need to test all the lines where both premises, there are two premises here, so let's only consider those lines where both premises are true. So generally here it is, your premises are P and P implies Q. This is important line. This line is irrelevant, I will even erase it because P implies Q is not true, so here I don't care if conclusion is true or not. So this line is really not obligatory for us. What about this one? The same thing here. And the same thing here because P is not true. So generally, there is only one line that's obligatory for us, and that is the line where both P, the only line where P and P implies Q are both true. So whenever all the premises are true, that happens only in one line, and on that line is the only place where I check my conclusion, which is just Q. Q is true, so this is a valid inference. This is a famous inference, it's called Modus ponens. And this is one of the main rules of inference. This is the way how we actually extend our knowledge, because we have a knowledge that, so if you think of our knowledge as being P is the current knowledge, then how do we expand the knowledge? Here is our current knowledge. And then we show actually that from our current knowledge we can deduce the new knowledge. Now we expand that, we accept that new knowledge into our body of common knowledge. So this is a really very, very important rule, but that's what it means. The question is, why is then this so important for us? Because if formally, so this is a formal definition, it could be checked very precisely, so now we are convinced that this is a valid inference, and then we believe that whenever our inference is valid, then whenever we use that to make conclusions, that our argument is correct. We don't, of course, when we speak, even when I speak now, we don't carefully draw these connections between premises and conclusions, so there is lots of the context behind, but we always say in mathematics, we can justify if challenged. Here is another example that also famous, and that would be another example. This one's called Modus tollens. So we have P implies Q, and not Q, we conclude not P. Basically this is a combination of contraposition and modus ponens, because if you take P implies Q and you flip it by contraposition to get not Q implies not P, then you use modus ponens. From not Q you will get not P. So this is another very famous rule of inference, and as I said, I'm not going to make a table, but if you make a table you can easily justify why is it true. Let's make something that's a little bit more substantial. Here's another example. So rule says P or Q, P P implies R, Q implies R, then R. Let's first see if this is a correct inference rule. Let me erase the other one. So first let's check if it's a valid inference and then discuss its importance. So we'll just make a table. As I said, that's the simplest way to test validness of a rule of inference. So we go here, 2 for T's, for S, then we go 2, 2, 2. And then we alternate completely. So here are all the 8 inferences. And then we just place there all the premises of P or Q. P implies R, Q implies R, and then I can read it to the left, but just I'll copy R so that I have them as a conclusion. So R will, so what do we get here? P or Q is through here, through here, through here, through here, through here. False and through is through, and here it's false. Here are 8 lines. P implies R. This is through here, false here, through here, false here, and through here, because when P is false, everything is true. Then Q implies R. So when Q is through, we get true, we get false here, we get through here. We'll get through because Q was false. 2 implies true is true, 2 implies false is false, false implies true is true, this is true. And as I said, I'll just maybe copy R kind of, it's at the end, so there's the same line as there. It's really redundant, but it might help us to kind of have it at the end of the story. False. Alright, so generally to check if the inference is valid, we need only to consider the lines where all the premises are true. So if you look at this line, this is a line that needs to be checked. Here are my 3 premises. This one no, because some premises are not correct. This is the line that needs to be checked, not this one. This is the line to be checked, not this one, not this one. So there are just 3 lines that need to be checked. So these are the lines where all the premises are true, and then we need to check if the conclusion, which is R, is true. Yes, yes, yes. So in all 3 relevant lines, our conclusion is true. This inference is valid. By the way, in this methodology, there is no dilemma. We don't need to convince anyone anything. We just make a table, we check things, we can program it easily, and that's it. Why is this now important for us? Because something that we hopefully believe as being kind of the basis of a good argument, now we can use this in the following way. So it's called actually argument by cases. So it says, if we know that one of the P and that P is true or Q is true, so those are the cases. Cases are P and Q. So if we know that one of the cases must take place, sorry, so one of the cases must take place, and if each of them implies R, then R is unconditionally true. And that's the argument we use very often. That's, as I said, argument by cases. And let me give you one example how we use that argument. So this is again the example from the note. From the notes, example 132. It says for every real number, number x, we have x squared is greater than or equals 0. So what do we do here? So in that proof, we have two cases. Case 1 is x is less than 0. Case 2 is x is greater than or equals 0. And if we think of this as our p and this is our q, then we have p or q. That means we know that each real number is either less than 0 or greater than or equal to 0. And then what? For example, we are maybe more familiar with numbers that are greater than or equal to 0. So from the table, we know that x equals a, where a is positive number, and then we have a times a equals a squared is greater than or equal to 0, where a is greater or equal to 0. Here, if x is less than 0, then we say x equals minus a, where a is greater or equal to 0. So we have x times x is negative a times negative a, which is a square, which is greater or equal to 0. So you see each, so this is like, so x, this is r. So here we prove that p implies r. Here we prove that q implies r. We have p or q. So conclusion is just r. And that's it. That x squared is greater or equal to 0. Of course, here I called some facts that that square of a positive number is positive. That needs to be developed from somewhere else. So this is just the last part of that proof that was used here. One more important rule of inference. Let me squeeze it in here. Is argument by contradiction. Contradiction. And that would be, we said the following: if not p implies contradiction, then p. And we'll have the whole section devoted to this argument later on in the course. But and it's very easy to justify that this is correct, because there are only two lines in the table. And that's what justifies something that we'll use quite often. It says the following: if we want to prove p, then what we do very often, we assume negation of that statement, not p, and if that helps us to reach contradiction, which is something that's always false, then that justifies that p itself is true. Like if not p got us in trouble, then it must be that not p was wrong, and if not p is wrong, that means that p is correct. There's lots of discussion, philosophical and logical, about this, but as I said, this is a fairly simple rule of inference, and let me use it here in one argument from geometry, actually a little bit more, not subtle, but slightly more involving argument. What would that be? For example, proof from geometry example. That would be 133. It says the following: if a line does not belong to a plane and it is parallel to a line in that plane, then the line is parallel to the plane itself. Here is a statement from basic geometry books. Let me just draw a picture to illustrate what they want to say. So here is a plane, let me call it alpha. And let this be a line B. And then let us assume that that line B is parallel to line A that belongs to the plane. So we know that A belongs to the plane like it's a subset of the plane. You see the sign for subset. We'll talk about it in chapter 3. So A is like a subset plane, and we also know that A is parallel to B. And we need to prove that B is parallel to alpha. So I'll put question mark there because, so these are the things that we can use. These are our assumptions, our premises, and we need to conclude that B is parallel to alpha. So we'll argue by contradiction, so we'll assume that premises are true, but that B is not parallel to alpha. So argue by contradiction. So assume that a subset of alpha B is parallel to A, but B is not parallel to alpha. So we assume to the contrary, that these two are not providing necessarily that B is parallel to alpha. But why would that lead to a contradiction? If B is not parallel to alpha, that means that B intersects alpha. Because every line in the plane either have points in common or not, and the line does not belong to a plane. So if it doesn't belong to a plane and it's not parallel, then it must intersect. So generally, a picture looks now a little different. And let's see why is that not possible. So B is somewhere here, so B is hitting alpha somewhere. Okay. But then what do we do? Here is that A that was already there. Then there is one theorem from geometry that says that two parallel lines determine a plane. So since B and A are parallel, there is a plane, let me call it the beta. So beta is the plane containing A and B. Here is the plane, green plane, containing A and B. Okay. But then what? Oh, I forgot to do something, sorry. B intersects alpha. If it intersects it, I should label that point. So that's a point. Let me call it A. At a point, for example, A. So we just named that intersection. All right, back to the main argument. Beta is the plane containing A and B. And then what happens? Beta and alpha. So what? Since B is subset of beta, because beta contains B, then B intersection alpha is the subset of beta intersection alpha. So B intersection alpha, that's point A belongs to beta intersection alpha. So beta and alpha do intersect. Okay. And then what? Then beta intersection alpha is, so intersection of two planes is a line. So beta intersection alpha is a line. Which line is it? That's it is actually A. Why? Because A belongs to beta and A belongs to alpha. So basically beta intersection alpha is A. So generally what? Since capital A belongs to beta intersection alpha, capital A belongs to A. So generally what means is that A has to go through. So this argument just specified that line A contains A, and here is the contradiction. Why is that a contradiction? Because we assume that A and B are parallel. And now they have point in common, contradicting the fact that A and B are parallel. So here it is. That contradiction so generally confirms that it cannot happen that B intersects alpha, B has to be parallel to alpha. So this is like a little more involving argument. Of course, there are many pieces where we just used some known facts from geometry. All right, and one more detail at the end of the section. There is one nice application that's from Epp's book, where generally she kind of combined one argument into the like detective story. So you can read, I'm not going to put the text on the board, so that's example 134. Example 134. So there is a line of information that, so it's a story about famous detective. It's actually Hercule Poirot, but she just changed it to Hercule. Wow, that's how she now renamed the detective, or gave a different name, and then from the facts they want that the detective collected, he wants to make conclusion. And of course, facts don't look like this in real life, but this is just a little logical exercise. So in part A, they say that Lord Heselton, the murder man, someone was murdered, that's Lord Heselton, and he was killed by a blow on the head with a brass candlestick. So Lord Heselton was killed. We actually didn't use source of how he was killed. And then what? Then each of the lines has information about different persons, but there are two types of informations. Where were they at the time of the murder, and who might be a possible murderer. So, so what we did solving this problem, we just recorded this in a more concise way. And then here is the convention I use, so that that concise version is fairly close to the text. On the other hand, is more transparent than long sentences. So if you read the B, it says that Lady Hazelton or a maid Sarah was in the dining room at the time of the murder. So we can say, I don't know if I have labeled it the same way, but I'll say Lady Hazelton or Sarah. I used small letters, small font for position, and big font. So this is Lady Hazelton was somewhere. So she's always in the dining room. So information is never, place is never changed for the same person. So this is position about Lady Hazelton, and this is position of Sarah, that they were in the dining room. And then C says, if a cook was in the kitchen, so I'll say the cook. I'm not saying in the kitchen because cook is only in the kitchen. I mean mentioned in the text at the time of the murder, then the butler killed. So there I put butler in capital B because that's about, it's not about position, but about committing the murder. Part D says, Lady Hazelton was in the dining room, which is LH. By the way, this is Lord Hazelton, so that's just that portion that confuses. Lady Hazelton was in the dining room, so that's the same meaning as before. Then the chauffeur killed, so we'll put chauffeur here in capitals. And then if the cook was not in the kitchen, so that would be not cook, because it's negation of the same statement. Then Sarah was not in the dining room, so that means not Sarah. So this is the same, so Sarah in the dining room, Sarah in the dining room is the same statement. And then finally F, if Sarah was in the dining room, then the wine steward. So here it is. Why is this better than text? Because it's kind of more transparent, and we can see that some statements were repeated more than once. So what is the way to make a conclusion from here? So now we can start using our knowledge of logic, because what? Using contraposition of this, we conclude that S implies C. I just flipped them and erased negation or added double negation, which is the same. But then, look at this. Now this line and this line here, but because of transitivity of implication, let me do the same in two lines, since I started with that. So Sarah implies C, whatever that C is, cook was somewhere, which is Sarah implies C, C implies B, so from those two I can conclude that S implies B. That's called transitivity of implication. S implies C, C implies B, so S implies B. But now look at this, I'll just copy below. S implies WS, but then what would happen? So from here I would conclude that S would imply butler and wine steward. It's called, because it implies both of them, implies their connection, but this is contradiction. Why? Because from here we would get that there are two murderers and there's only one murderer. So what is that telling you? Since this is false, then S is also false. So from here we conclude that it's not S. Not that. I should use the same letter. Not S. And now what? What happens now? Now from line B, since we know that it's LH or S, LH or S, so since one of them must be true and S is not true, we conclude that it is LH. So Lady Hazelton was in the dining room. And finally, Lady Hazelton in dining room implies chauffeur was the killer. So using modus ponens, we conclude the chauffeur was a killer. So this is a nice, simple exercise, where actually everything was about doing a good bookkeeping, and then we had very quickly somehow the opening, for example. This was a natural move to just flip them, and so to reduce number of negations, and then things started to connect with each other. And I think it wasn't too complicated, but it was showing how if you write it in a transparent way and you use basic logic rules, you can reach the conclusion. You will see in the homework, there is that Einstein puzzle. I just rephrased it in different language. That one is very complicated. You need lots of cases, lots of reasoning, but I think it's a good exercise. Of course, don't expect that to show up on any kind of exam or any kind of assessment, but I think it's a good exercise in your problem solving.